Hello and welcome to this video about our 2017 Neuro-Image paper about Bayesian model averaging. So this paper was a follow-up to earlier work about Bayesian model selection for general linear models, or GLMs, in fMRI data analysis, in which, as we know, the voxelized Bode signal is decomposed into experimental conditions and potential compounds, weighted by some regression coefficients beta, plus some noise, which is also in the data and not composed by our model. In recent work, we have developed cross-validated Bayesian model selection, or cvBMS, which analyzes fMRI data from a single subject using different models to come up with voxel-wise log model evidences, or LMEs, as a model quality measure. This information can then be taken to the second level to come up with voxel-wise model frequency maps, which inform us about the optimal model in a studied sample. Now, if the regressors of interest are differing between the models, as is the case in non-nested model comparisons, then cvBMS is the method of choice. If, however, we have the same regressors of interest in all the models, and the models are only differing by which additional regressors are contained in the design matrix, then there is a more powerful approach based on Bayesian model averaging. And in Bayesian model averaging, the idea is to take the log model evidence and use it to calculate posterior model probabilities that, for example, model I is the true model given the measured data. The average model parameter estimates are then calculated as a weighted sum over the estimates from all the individual models I, where the weighting coefficients are just the posterior model probabilities. So in this way, we are accounting for uncertainty about the modeling approach, and models which are more likely a posteriori contribute stronger to the final parameters, which supposedly makes them more precise. So if we have a set of common regressors to which different sets of additional regressors are added to constitute a model space, we use GLM estimation to come up with parameter estimates for the common regressors, as well as posterior probability maps. And then we can perform Bayesian model averaging to calculate average parameters for the common regressors. For empirical validation, we here used a conflict adaptation paradigm in which subjects were presented with those flanker type stimuli, either congruent or incongruent, and to which different rules had to be applied. So the stimulus response mapping was either like this, or it was like that. First, there was always an auditory cue signaling the subject which rule to apply. Then there was a delay phase in which subjects could prepare for this task. Then there was a main block in which 10 trials from this experimental condition were presented. And then there was a visual feedback after each block. So for this fMRI paradigm, we can use a model which includes 4 regressors for the blocks from the 4 experimental conditions, 2 regressors from the delay phases belonging to either stay blocks using the same rule as before, or switch blocks using a different rule than before. To this basic model setup, we can either add regressors for the Q phases coming before the delay phases, or regressors for the first trials from the blocks coming after the delay phases to account for further neural processes. Or we can add both, which again gives us a model space of 4 different GLMs. In statistical inference, we were interested in activity differences between stay and switch blocks with respect to the delay phases. And there in fact existed such an effect. And if we accessed this effect using the individual first level models, we were not able to find any activation using the most complex model, which included all the variables of no interest. If we then performed cvBMS, and used each model only in those voxels where it was considered optimal, we were able to demonstrate the effect using one of the models, but it was not the most complex one. Finally, if we used the average model parameter estimates, we were also able to identify the effect in the left primary motor cortex. So, to sum up, if we're looking for activity differences between stay and switch blocks, we can find them using different individual models, and the Bayesian model averages make a nice spatial compromise between the individual models clusters. So with that, I want to say thank you, and if you want to know more, please click on the link in the description to access a free PDF of the paper. Thank you very much.